What's going on, folks? In this video, I'm going to talk about how we compile software. It's going to be a little bit specific to C and C++ programmers, but the process applies to pretty much every language that you use, whether it's Java, JavaScript, Python. This process of how do we take code from a source file, how does our computer parse that code to make sure that it's valid, check for errors, and then ultimately generate a program that runs. So let's go ahead and walk through the compilation pipeline. So what I'm going to talk about in this video is this basic process where we're going to start off with some source file here, source.c or CPP. And I'll use CPP for this example for C++. And this is where we start here, just our text file that we write. And then we actually send our code into the next stage, which is known as the preprocessor. And the preprocessor is used for things that start with the pound symbol. So you do pound include, pound define, or pound if statements in your code. So if you've ever seen these in C or C++ code and want to know what they mean, then we're going to walk through that process. Afterwards, our preprocessor then takes our source file, so source.i, and then finally we get to the compiler. And the compiler's job is to generate some sort of intermediate representation of your code and then some sort of assembly of your code. So here's where you actually get the ones and zeros for your machine, or often you'll get the assembly output in some form. So maybe an instruction like move some value like 1 to some register. So that's what we're getting in this stage. And then in the next stage, you might have an assembler, such as ASM, that's taking in your source.s file, and that's actually generating valid machine code for your architecture. So whatever computer you're running on here, maybe it's a fancy Mac M1, maybe it's an Intel machine, maybe it's an ARM machine, whatever this machine is here that you're using here to run your program, the code that's compiled from this assembler is assembled and an object or binary file is created. So that's this next step here. So I get a source.o file. And then we're not quite done yet. Most times when we're working in C and C++ here, we have to go through one more stage, and that's the linker stage. So here's our linker, and this is where we bring in other libraries. And they might be other .o files, like if you're using commands like printf, for example. If you're a C programmer, you'll bring in printf.o, some other assembly file that's been compiled to an object file and is going to get glued into the final executable file. And then you might also have other types of files linked in by the dynamic linker. So this part's the static linker, and this part's the dynamic linker. And this is if you're running on a machine like a Linux machine, which I'm going to demonstrate. These are your .so files, your shared libraries that are dynamically loaded into your program. Windows users might be familiar with DLLs, Mac users .dylib, but these are files or libraries that are going to be shared amongst many executables and can be loaded at runtime. They're compiled in a slightly different way that I won't address directly here, but I'll show you how to figure out which those libraries are. But those are brought in during the linking stage. And it's important to take a look at this linking stage here because oftentimes you might have different errors in your linker that you have to resolve than your code when you're compiling, for example. So it's just something to keep in mind when you're doing some bug hunting. If you've ever seen an error like undefined reference, that's usually because something wrong is going on in your linker. Okay, so that's the idea there. So what I will now show is finally, after we get through the linking stage, then we have our executable. So whatever we want to call it. In Linux, we would just do /source. Windows users would know this as source.exe. Mac users maybe source.app, but that's the final program that you get to double click on or run in the terminal and compile your code. So what I want to do is just write a simple hello world, talk about some of the different stages individually in this lesson and how you can peek inside and see what each of the stages are doing, and then also talk a little bit about some of the common flags that you might pass to a compiler for working with libraries in this linking stage. So the -I flag, -L, -l, these common flags that you'll often see, where they come into play, and we'll build a little project to do that. So if I've enticed you to watch the rest of the video, it'll be a full lesson, but hopefully this is a video that'll take care of problems and bugs, just understanding how you build software into the future. So with that said, let's go ahead and dive in a little bit. Okay, so I've highlighted the compilation pipeline here. The things we're going to talk about, the different flags, and this whole pipeline here. But in order to get started, we're going to need to have a file to work with and compile. So what I've done is just created a directory here. It's empty right now, and I'm just going to create a C++ file. You can follow along in either C or C++, and in fact, you can probably follow along in many other compiled languages that compile things to executable. Maybe languages like the D language or Pascal, for example. But we're going to use C and C++. So what I'm going to do on the right side of the screen, again, is just create a file here. I'm going to call it source.cpp. And this is going to be a file that contains a piece of code in it. And I'm just going to write a little function here. I'm just going to call it add. It's just going to take an integer, a and b, and just return the sum of these values, a plus b. It's a very simple function here. And let's go ahead and just try to compile this file here. So I'll leave the source code on the top here, and I'm going to split my window here using tmux so that we can see things in both views here. So I can just type in g++, and then I can type in the file that we want to compile, which is just going to be source here, and I can hit enter. And you're going to see that's going to give some errors about undefined reference to main and so on, because we need a main function or an entry in our program. So let's go ahead and write out the rest of this program here. Because what I'm going to do, just to sketch things out a little bit, is I'm going to create 3 files here. I'm going to create source.cpp, I'm going to create source.hpp, and then I'll create a main.cpp file. The main.cpp file will be our entry. The source.hpp is going to be a file that we would include to get some functionality. So this is our interface or our functions. And our source.cpp is going to be an implementation. And I'll just work with something very simple here like that add function here. So let's go ahead and create those files here. So we've got our source file here. So I'll go ahead and just annotate it here, just in case you're not clear with Vim what's going on here. And we'll need to create our other files here. So let's go ahead and split this window here and create source.hpp and create the source here. I'll make this a little bit smaller just so you can fit everything on this window here. Source.hpp. And all this is going to do is make a note that there is a function called add here, and that it takes in a integer, 2 integers as the parameters, and returns an integer as the result, as we're showing here. So it's a relatively trivial program here. Okay, so let me go ahead and just leave this here. And I'll go ahead and create one more file here. And this is going to be our main.cpp. So our main CPP is going to be our entry point into the program. And we're just going to return 0. And I'm going to include our source.hpp file. So I need to include source.hpp. Okay, and here we have all of our files included. And we can see them all here. And there really isn't too much to them. They're relatively straightforward source files here. So let's go ahead and try now to compile our program. And I'm going to just start with the main for now here. Okay, so I'll do G++ and our main file and hit enter. Usually when we do this, we get an a.out file, and I can run that a.out, and it doesn't really do anything now, it just returns 0. So we'll want to actually return a result or print something out. But what is actually going on here, though, is I want to take a closer look at this first stage here. Because we've compiled our file here, we have gotten a binary, but all of these steps here in between have actually been hidden from us. So what seems like magic, all these different steps have been omitted from us, and we've just gone from our source file to the final executable. And this is great, but often when we have to debug or build larger software, it's important to know how each of these steps all fit together. So let's go ahead and look at the first stage, which is the preprocessor here. So while we're analyzing the preprocessor, how can we see what's going on in this main file here? I'm going to make this a little bit smaller here just so you can see everything on the screen for just a moment here. In fact, that might be a little bit too small, so let me just leave it at medium font here. But the idea is when I just type in G++, this is the compiler, and this is the file that we're compiling ultimately to an executable. And by default, it'll be a.out if we don't give it a name. Let's give it a name here, -o, and prog for program here. And that will again generate this executable file here. So I can remove the a.out and just have that here. So this is the file that we can execute. But again, how did we get there? So from our main file, the preprocessor step will actually handle all of the things that begin with a pound symbol, things like the include. And this is one way that we can do conditional compilation. That is to bring in files or source code that we need, or perhaps evaluate things at compile time, so we can have if or end if statements. But what I want to show you here is just the fact that if I run our main here, and I pass the argument -e, this will output what the preprocessor sees. So you'll notice that this is just dumping to the terminal the text here. You can see our int main here, because we compiled our main source file, but you can also see that this int add function, which comes from our source.hbp, was pasted in its place. So anytime you see include, you're literally doing a copy and paste. Okay, so that's important to understand that, because that's how we know that this function would be available here, this add function. So now in my main source code, let me go ahead and we can make a call to our add function and do 2 and 3 here. So now if I run this code and try to compile it, it will it'll still give an error here, but it knows that this function is available here. It says it's just undefined here. So we need to do a few more steps. But again, if I run it in the preprocessor, we'll see, okay, this function exists somewhere. And if I want to promise that it exists somewhere and that the implementation will be included, I can type in extern in to be very explicit about it. But by default, all these functions are externally available somewhere. So this extern can be omitted. That's basically saying, yeah, we promise that this function's available. Its definition will be in another file. So for example, in the source.cpp file. So again, I can still try to compile this. It's still going to complain and say an undefined reference to add int because it knows about it. It didn't give us a syntax error, but later on in the process, it's saying, yeah, we don't know about this. So for example, just to show the difference on the errors, if I don't include this file and I compile it, it'll say error, add was not declared in this scope, because it doesn't know about the function add. But when I include this, it'll say, yeah, of course, we know about add. It's still here. It's not a syntax error. We know that function is available, but it's just undefined. How do we do the add? And that's in the source.cpp. So we can resolve this by adding in the source.cpp file here. And then if I run it, we'll say, okay, compile main.cpp and source.cpp. So now I know about the implementation. So that's why you'll often see programmers compile things all in one line like this, or sometimes if you're a little bit lazy, you can just put a wildcard here and do star.cpp, and that'll compile all the C++ files together. I don't particularly like this. It's a shortcut, but I want to know exactly what files I'm compiling. So I just write them all out one at a time. Okay, but back to this preprocessor idea, where I'm showing that during the preprocessing stage, when I just emit things with -E, I'm essentially, again, just doing a copy and paste of whatever is inside this file into my file that I'm trying to compile. So what happens if I, for instance, accidentally include the same file twice? Whether by accident here or, again, in a very large project that this could occur. So if I run my preprocessor, you'll see that I have extern int add included here 2 times. So I'm going to go back and do our trick and say, well, okay, we wanted to build this, so I have main.cpp and source.cpp. I hit enter here, and I try to run it, and this time it's actually okay. But the danger here is that if you include the same file twice, and let me make sure I've saved this, then it might get confused as to the definitions that you have here. So, for example, in our add function here, I will also include source.hpp because we're including the definition here. And then anytime we compile this file, what we really want to do is include the header file with it. Okay, so let's go ahead and compile. And oops, looks like I added an additional token here. So let me just save. And if I rerun this, it looks like it's doing okay here. So it's not complaining about multiple definitions or any of this issue. But this is the danger that it could. And I'll show you a common error that you're going to find in C++ projects where a lot of folks will just go ahead and define implementations or when you're declaring a class, for example, in the HPP file. So again, let's see what happens if we try to compile. And this time you'll get the error that says redefinition of int add here. Because we've included this file multiple times in multiple places where it's just doing the include here and essentially copy and paste here. So you get sort of these weird issues here. So even if I'm not doing anything in my source file here, let's just comment out everything just to be clear what's going on here. And I'll try to build this. And in my main file above here, where I'm still including things twice, let's see what the preprocessor gives us. So if I just do -E and then the main file, you can see that it's including in this file 2 different times here. So it's copying in 1 time here from the source HPP, and then it's again coming down here and copying again. So you get multiple definitions here. And again, this will happen multiple times if you have functions defined in your headers or any implementation. Like if I create a class here for some object or sort of set up the blueprint, you'll get multiple definition errors here, okay? So we're gonna wanna avoid doing that. Now, an easy way to avoid worrying about these definitions being included multiple times is to use something called a header guard. So this is, again, the preprocessor where I'm gonna say if not defined source HPP, and I can make up whatever I want this symbol to be, define that symbol, HPP, and then just do end if. Okay, so that way we're taking advantage of the preprocessor and saying, hey, if I've already defined this file 1 time, don't include it 2 times. Okay, so let's go ahead and try this now. So I'll compile here, and it did compile, and I'll just run it through the preprocessor. And if I scroll through this time, you'll see that the add is only brought in once. Even if I've included the file multiple times here, or if I've included it in other files, it's only brought in 1 time into our project. So that's what we want to do with the preprocessor, and a common error that we have with multiple definitions. Okay, now that we've talked about the preprocessor a little bit, and the preprocessor is quite powerful, but the most important thing I want to show you is just this -E option so you can see exactly what's going on. And in fact, things can get quite heavy here when you include some of the standard libraries. So let's just go ahead and include something like IOStream so that we can do output in our main file. do the output, and if I scroll through this, you're going to see a whole bunch of other stuff because I've got all the input-output stream library here. If you actually search through this, you'll find your functions like cout, cin, and so on. Okay, so again, that's the preprocessor step. Okay, so now let's talk about the compiler step. And for this step, I want to talk a little bit about what your compiler is actually doing with your code here. So that's this step here. And again, the goal is for most compilers is to transform your program. So if I just have some simple expression over here, for example, 2 plus 2 somewhere in your code, say it's part of your code somewhere, int x equals 2 plus 2. What this is really doing is transforming this to some internal representation in your program. So it's going to take this assignment here, perhaps from the x equals, and it's going to say, okay, we have x here, it's equal to some expression, and it's essentially building a tree. And depending on, you can dive a little bit into a compiler's book here, and you'll get either an abstract syntax tree or a concrete syntax tree, that's what it's called. But you'll get some sort of tree here that is then showing, okay, we have some plus here, and then a 2, and then a 2. And then I'm essentially walking through this tree and sort of doing a traversal here in this direction here. And I'm getting things like x equals, this is the next thing I hit, and then I go down here as far as I can, 2, and then I traverse back up here to the plus, and then back down here to the 2, and I get this expression here. And of course we have our assignment here. So this tree sort of continues here, right? This is part of some integer here that we're traversing to. And these trees can be quite large. We usually don't have to worry about them, but this is what your program's doing. It's building this internal tree, walking through this tree, and this is also how you're finding your errors. So for example, if I had already redefined x, for instance, and it walks down this tree and says, hey, you've already done x equals something, then it would say, well, x is not valid in this scope, and it would sort of catch it here. Maybe there's more line information, this is on line 1, and that's how it tells you syntax error on line 1, and so on. So you can actually dump out the syntax trees. So let me go ahead and just, again, in showing you what exactly is going on in this compilation stage, show you a little bit of this. So depending on the compiler you're going to use, there's going to be different ways to do it. But let me go ahead and just show how to do it with G++. So you can see what this syntax tree or internal representation is. Again, this isn't something you have to memorize, but just something that I want to show you. So fdump tree all graph. I'm going to do it with -g, so you get the debugging information. And let's see, main.cpp and our source.cpp. So however we are building the program. And when I type this in, what you're going to notice is next time I look at my contents here is I have a ton of files here. And what I actually want to look at is these dot files here, and I can visualize them. So different tools like GraphViz or on Linux, xdot can let you look at some of these files here. So if I look through these, there's main.cpp, and then there's some with a dot here. Again, I just want to look at the ones with the dot here. And again, there's all sorts of different versions of these and for specific functions that we might use. I'm just going to pick one here that I've picked out, but you'd have to sort of look through most of them to see what's going on. But again, I just want to show you what's going on here and see if you see anything that looks familiar. So if I see this main function, for instance, well, that's something, and we enter into our function. And within this block of code here, you'll see this add 2, 3. Well, that's one of the functions that we called here. And this returns, some value from it in some location, _3, and then we exit. So again, this isn't really for us to read here, but this is, more for a compiler person to understand what's going on at each stage. And you might be interested in using this as part of your analysis or just understanding what's going on. But the basic idea is this is how your code's parsed. It builds these trees for you to look through. And this could be one way to visualize it, and it's pretty neat. Okay, so that's the compilation stage, and there's many stages, and that's more sort of on the front end side of parsing things and checking or verifying in the language's grammar that these are legal statements. But the other things that would take place too is the code generation step. So that gets us to this source step here, which I want to take us to. And what this is doing is, again, it's walking through this tree, but it's very simple in a way, right? We can see int and then equals and then x. These are very primitive sort of operations, and we can break those down into the corresponding assembly instructions. And our assembly instructions is just a textual representation. So textual representation of machine code that our systems understand. Okay, so this is the idea of what's going on in the compilation stage. So let's go ahead and look at how do we get the assembly out of our compiler. And typically this is a tool that's bundled with G++. It's actually the gas assembler. That's the default one that it uses to my knowledge. And there could be other assemblers that could be used, but let's just go ahead and look at how do we get that assembly code out. So in order to do this, we just do G++ -s and then where our file is. Let's just work with the main file here. And when I do that, it's just going to, if I list out here, it'll generate a .s file for us, okay? And this s file is the assembly file. So let's go ahead and open that up here. Okay, so here it is. Here's the file. And some of this we can understand. We can see things like the file name. The .text section is where we have our actual source code. Here's something called a label here. And again, this is something that we could read or write. We usually don't have to because we're using a higher level language, C++ versus assembly, which would be considered much lower level. And here's the different kinds of instructions. And you can see there's actually a call to something that looks like an add function that takes in 2 integers. That's why there's 2 i's here. Underscore Z3 means that this function is returning an integer. So there is some sort of mapping. Again, luckily we don't usually have to understand what this is, but it's very simple. One thing or one sort of operations happening per line, and this can be translated into the machine code that your machine ultimately understands. Okay, we can understand this, but if we open up the program that we compiled, we can't understand this, right? This is all binary code, but we can understand the assembly when we look at it in that fashion. Okay, so that's really what our compiler is doing. It's getting us to the separate assembly representation after parsing and making sure that we have a valid piece of code, and then we can assemble something called a .o file. Okay, so let's actually do that in a step here, and we can actually just build our program and export out this .o file here using G++. There's other tools to do it. You can use a linker here, but I just want to show you how to compile directly to that .o file and investigate it just a little bit. So, for example, if we want to compile out our main file, the .o file here, before it's executable, we could try something like this. Let's see what happens if we try to do this. Now this is still going to fail to compile because it needs that source file. So we're still doing something similar here where we want to build out maybe some object file here. That's all the machine code needed here. So again, our compiler stage needs to pass, and we still need to have available all of our machine code. Otherwise, it's going to complain about some of this. So I can just do this compilation here with the 2 CPP files. Okay, so I just do that. And then if I list out here, I'll have my .o file here. Okay, and I can try, to execute it. It doesn't really do anything here at this point here, but I've just outputted as a .o file. And then I could take it in as a O file, output it again as our program here. But I would have to do this in sort of 2 separate stages and sort of glue everything together in the linking stage. Okay, so how would I just compile one of these together in just sort of one step at a time. Because we can't really do this. It doesn't really make sense because we already have the executable here. So what I do instead is I just do G++ and I just do -C to compile that file, okay? And this way it'll say, you know, is this file here, and I'll go up to our main file here, is this a valid file here? You know, does it seem like it could work? It doesn't matter if we have the implementation or all the information, it just matters that we know that this function's externally available somewhere, and we'll worry about that later when we're building the final executable. So if I do this step here, then that will, again, just make the .o file, but this isn't the executable here. This is just some object file, some collection of machine code. And then I'm going to do the same thing here for our source file here, our source.cpp. And then I'll also get, if I list out the source file, let me just do this in one line here. Oops. List out source.o. I do have it here. Okay, I've got all the other control flow graph and all the stuff that we output for the visualization. But here's the O file. So now I can actually just do G++, main.o, source.o, and then output it as the program here. Okay, and then this will run. Again, it doesn't do anything interesting yet, but it's taking the two object files and gluing them together. And that step is actually being done by the linker, which is gluing things together one step at a time. Okay, so again, at this stage, we're linking things together behind the scenes, and I just want to show a little bit more about what is going on here. And we could actually try to sort of take a peek at what else is being brought in with this program when we're compiling the object files here to prog, because we'd expect at least main and source.o. So a tool I like to use first and foremost is just to look at these object files and see what's inside of them. So let's go ahead and see what's inside of source.o. And this tool is called objdump, and it's just going to dump out a bunch of information. So here's the sort of arguments that can be brought out here. And you can kind of explore this. There's similar tools on Mac. There's OTool, and Windows has DLL, dependency walker to see some of the files. So some of these things where you can just get a little peek here. I'm going to use -T, and that's going to tell me about the different symbols that are in this source file. And the one in particular that I'm interested in is I can see here on this last row here, I have that little add function. I know it's a function because I see -F here. That's how I was able to quickly find it here. It's part of the program, and it just tells me where it lives in this binary file. Because again, if I look at the files that are created source.o, they're not really human readable, right? They're just binary blobs of data. So I can just see inside of them with this objdump tool, which knows how to parse those blobs of data to something that we can read here. So anyway, that's one way to look at what's going. And then what we're doing, again, is we're gluing together our files. So if I look at objdump.t and I try to look at our program here, let's see if I can recompile it here and see if I can get a look here. So here's our full program that we compiled here. And depending on if you compiled with debug symbols, you might be able to see a little bit better into it. We can see that there is source.cpp is part of it, main.cpp is part of it, and so on. So you can see some of these details and peek into your binaries just to see that those two files were indeed glued together during the compilation process. So again, that's helpful to see what's happening. And again, behind the scenes, what's happening is the linker is gluing together all of these .o files here. So we've got our source.o, and in our example here, our main.o as well. So any number of files here are coming into the linker, whether they're in your operating system or some library or ones that we're compiling, okay, into this linking stage. Now we can have other libraries also dynamically linked in. So for example, let's make our executable a little bit more interesting. And let's finally print out some value here. So we'll use the standard cout function here to finally print out our result here and maybe end here. And let's just compile this again from scratch here. So I'll recompile it. I'll run it to make sure it's working here. And let's see, it should be printing out the result of our function here, 5. And let me make sure I am compiling not our object files, but our CPP files, just to do this all in one step here. And then I'll run our program here, and it's indeed printing out 5 here. So beautiful. So now that we've used this function, though, where does this come from? Because we've included the header file here. If I look up, we have IOStream, which is a standard C++ library here that we've included. So where does that come from? Where's the implementation? Well, there's a little tool here. I can use LDD that'll tell me where that comes from. So if I run LDD and then the program here, it tells me all the other libraries that it's bringing in or linking in at runtime. So when I start running my program here. So I see that one of these libraries is the standard C++ library. I can see where it's located, and this is what's being brought in. And then there's some other libraries here. It looks like libc, the math library, and some of these are by default here, okay, that are being brought into our program. And that's this sort of dynamic linking stage, files that end in .so. In other operating systems, they would end in .dll for our Windows users, .dylib for our Mac users, okay? And there could be, arbitrary extensions, but that's the convention. Okay, so that's the idea. And then once everything's linked in here, then again, we get our final source executable. So let me sort of summarize all that we've talked about. Again, this is a long video on compilation and how things work, but I think valuable to just understanding what's going on at each different stage here. And then we'll talk about some of these flags here, and I'll actually do an example that I'm like working on and download a library for us to try an example so we can see some different errors and debug a little bit. So we started with our source code that we had here. That's our files that we've just opened here, a really simple little project here where we've written one library with a little add function. We've run with our G++ in our preprocessor with -e so we can see what's going on in each of these files when we include them. And that's just doing a copy and paste, essentially, of the contents of things that are included or handling other conditional compilation things. And then we see that our compiler finally runs. Internally, it's building this tree of our source code so that we can detect syntax errors and then finally validate that we have a valid program. And you can, again, read a little bit more about these things and that it's a valid grammar in the language and so on. But it ultimately is just trying to generate this assembly code. Okay, and we could get to the assembly by doing the G++, the file that we want to run, and then -s here. And that'll give us the assembly output. Okay, and then finally, we looked at the linking stage where we were linking in either object files that we had compiled with -c to compile these one at a time if we wanted. And then we could glue them together, so the actual object files. So let me just do that here. So that was one way to glue things together. And the program works just the same. And then we looked at what was also happening at the dynamic linking stage with prog here. Okay, and some other handy tools like objdump just to see what's going on in some of these files here. And again, compiling with little debugging information can be helpful, right? So if I instead compile this with -g, for instance, and then run our objdump tool -t for the symbol table information, so I can see all the symbols here, you'll see what some of these functions are and where they come from and so on. Okay, so that's for you to explore a little bit later. Okay, so that's the sort of full process. So what I want to do now, though, is actually take a look at a library and then talk about how we include that library into our code, because we kind of got away with things easy here when I was running prog here. You can see that these were just default libraries that were included. I didn't have to tell it, hey, bring in the IOStream library. It just knew how to do that. So that was actually really nice that it was able to do that. So let's go ahead and explore that. And what I'm going to do is I'm going to open up a browser and just go to a library that I like using. This is the SFML graphics library, where you have a nice sort of game development and graphics framework here. And they have a little tutorial for getting set up on Linux, so I'll just briefly, I've already installed it, but I'll just run through it again here. So let me close these files out here. So what you would do is using your package manager if you're on Linux, or if you're on Mac, maybe Brew or Windows, you just can download it and get things set up here. I've already got it here, but that's all you need to do for the install. And essentially what this has done has installed some shared object files somewhere in our system, okay? And what we would have to do, so just scrolling through this, is let's just take a little project here, and let's just try to run it here. Okay, so I'm just going to call this one sfml.cpp. I'll just paste it in here. This is just our sort of hello world program here, if you want to take a peek at that. So let me go ahead and just save that. And then within this directory, I'm going to just try to compile it. So like what we've been doing. Let's do -g just to get some debugging information in the file, and just output it as prog. And you're going to see I'm in a little bit of a world of pain here because there are lots of errors here. Okay, syntactically, I can tell you the tutorial is correct. There aren't any syntax errors. I don't see anything here warning me that I made a error after I did this compile, but rather it says in function main undefined reference, undefined reference, undefined reference, undefined reference, and so on. And basically it's just saying, we can't find where these files are, or the implementations rather, okay? It tried its best to make a program, but we just can't execute it because we can't find the appropriate files or the implementations of these different functions. So the trick is we have to actually link in these libraries. And I do that with the -l flag and whatever the library name is. In this case, they're sfml-system. And if we have multiple ones, which we do, sfml-window-l sfml graphics. Okay, and I'll put this all on one line just so you can see it at the bottom here. And then if I hit enter, now it compiles, and now I run their sort of hello world program here where I get a little circle here, which is pretty cool. So what I've done here is I've told the linker, which is running as part of G++ when I compile it, I say, hey linker, bring in all these libraries, okay? And make sure that we link them in, right? So I can run this LDD command on our program again, and you're going to notice this time a whole bunch of other libraries here on the right-hand side of the screen here have been brought in. So I can even scroll up here. Let's see if we can find some of those ones that we included, like lib sfml system. Window is here, graphics in here. And we can see the actual location of where this is coming from. Okay, our package manager made it a little bit easy for us on Linux. So I want to show this in one more step, what you might do if you can't find that library. So for instance, if I just list that location here, all these libraries here, and let's see if I can find SFML here. I think it is lib SFML here. SFML here. So here's all the lib SFML libraries. They were installed in this location. So you might have to hunt for it or sort of query your package manager where these were installed. If you're on Windows or Mac, chances are you have all your .dylib, DLL, .so, whatever files installed somewhere. But you can see these. So in Linux, it happens to be that I didn't have to specify this path, but let me go ahead and just do it anyway, just to be explicit here when we compile. Because it's enough to just, on my system here, and I'll show you why in a moment, to just say link and find this library. But where is it actually? So that's where I can pass in another command line argument, or to this compiler, another flag, -L, and then this path to this file here. And it says, hey, look in this file, -L, for libraries that match this name, SFML system. By default, you don't have to type lib, it'll assume you've named them lib, so it's just looking for SFML-audio or SFML-graphics. The -L is sort of shorthand for that, okay? So if I hit enter here, this is still going to work. And again, why I didn't have to type this name out here is because the the compiler by default will look in a special variable on Linux called path. So if I echo out path here, you'll see that there are some default locations like /user. Let's see if I can find it here actually. There's a couple of them, but path is one of the locations where it'll default look in all these folders here until it finds the first match for SFML system or whatever it is. And it's looking at all these locations that are separated by a colon. Okay, Windows has something similar. It has environmental path variables that will look in by default to try to find libraries that you specify in your compiler. I believe Mac has something very similar. It has like a frameworks folder that you can look in by default. So that's the idea here with what's going on. Now the second thing you might also be wondering, because I had one other flag here, -I, and that's the include path. Okay, so for this SFML, you might have noticed that, hey, we didn't specify where this was. Okay, if you remember in our other programs here, and let me open up one of them here. I'll just split the window and put in the source. We just specified with the quotations, look, include, do the copy and paste of source.hpp. Okay, and it knew just within this directory, it was in source.hpp. So this might have been in /source, the current directory. I could have specified the whole name, whatever it is. This is on my home folder and the compile folder. This would also be valid, but typically we like the relative path. But again, when we include something, if we use the left, the lesser than and greater than sign here, or these wickets here, it says, hey, look in one of these system paths for a folder called SFML, and then within that, look for graphics.hpp. So that's the include path, okay? And again, I just want to be super explicit and say, okay, what if we didn't have this path and this was giving an error message? How would we compile this on the command line in all sort of one go? So let's go ahead and do that as well. So this time we have G++, the source file we want to compile, how we want to output it, the different libraries that we're linking in, where to find those libraries, and then again, we need to know about where these functions are. Okay, so let me go ahead and just I'm actually going to open up another terminal window here just so you can see here the actual location of where I would find this. And I just sort of have a hunch of where these things are. So if I cd into my user drive in ls, there is an include folder. This is usually where it's putting them. You can use tools like find and try to find graphics.hpp, for example, on your system, maybe from your home folder, but I know that they're usually in user. And then there's an include folder here. So if I ls here, there's a bunch of stuff. And then I can find, I can probably search through and find it, but I believe SFML is here. So if I scroll up, here it is. So I cd into the SFML directory, and there I can see the graphics.hpp. Okay, so if I wanted, I could specify this whole path. Let's go ahead and do it just for fun to see that it works here. So let me go ahead and just close that. And then I'll just paste it here because I just want to show you how this works. Just again, so you know exactly what's going on here. So it's in the SFML and then graphics.hpp. So I could do that. And if I hit enter, it still works. I'm just putting in the whole name to this thing. But again, it is looking on these system paths in user include. That was on my path directory, I believe, here. So if I look through here, I've got user games, user local bin, user/bin. I think I've got just /user in here, or one of these paths here. I think there's another one, but that's the idea. So again, what if I just wanted to specify this with graphics, for instance? So let me just compile this here, and it says, okay, we can't find the library. So in this case, I would just specify with -I, and then this path here, and then it would say, okay, compile with G++, debugging symbols, the source file we want, output it as a program, link in these libraries, find those libraries in this folder, and any header files that we include, Well, if you can't find them in the current directory, start looking in here. Start looking in /user/include/SFML. So again, if I look in /user/include/SFML, I can see that, oh, my compiler would be happy. It would then find graphics.hpp. This is now on the include path. You can think of it as almost pre-pending it or putting it in front of graphics.hpp, and anything that, again, is not in the directory, it would look inside there and try to find things, okay? So that's how you include files here. So for our flags, the dash include, and I'll just annotate these, include our library, so include directory, library directory, I'll put this in, and library files here, dynamically linked library files. Okay, so that's what's all over here. Okay, and I want to show this just in one more example because I'm showing this on Linux. Maybe you're on Windows or something. But when you're using IDEs and stuff, these details get hidden from you. It's the reason I like doing things on the command line so much. But you'll have these dialogues where you're going into the linker, the general settings, and then you're setting additional library directories. Well, that is that dash uppercase L here, wherever you installed it, okay? And then in the linker setting for input, these are your SFML graphics. In Windows, they just end in .lib. Same thing for the include directories here. Let's see, I didn't see a option here. Oh, here it is on this first one. So the C++, the general, additional include directories. This is just, it's hiding that capital dash I option, but it is putting it there. So I'll bring myself back on here for a moment, since you haven't seen me in a while, to say that, I really think it is important to be able to do it by command line, but then just also understand in tools like Visual Studio what they're actually doing for you here. Okay, so let's go ahead and just look at the Xcode one, because I think it's doing pretty much the same thing here on Mac here. Okay, just so you understand, you're setting up those exact same things. Here they might give you a nicer template here, but you can actually just specify things on the command line if you know where they live, these exact libraries that you have here. Okay, Mac might be a little bit weird. Sometimes they give you a framework thing, so you're doing -framework SFML window instead, but that's the idea. Okay, so with that said, I want to just go ahead and wrap us up here. I know it's a lot of stuff here, but this is the full compilation process, and it's something I see folks really struggle with when they're just getting started. And it's important to understand what's going on in C++ here. These same skills will also apply in Java, for instance, when you're compiling big projects together and things are going to bytecode. Well, it's not assembly, but it's a similar idea. And then you're sort of linking or gluing together lots of different pieces of source code, whether they're in source or binary. So it's just important to understand what these different steps are. So thanks for joining me for this lesson, folks. I hope it was really valuable for you in just understanding once and for all how to compile code with C and C++. You got to see the process, got to walk through some helpful tools, at least on Linux and exploring some other platforms. And then even with a practical example of using the SFML library, which might be a great one to practice on if you're just getting used to compiling code. So hope you enjoyed this, and we'll see you in the next one.